So last section, which I know I'm hearing in the hallway and on Facebook how much it is loved about slope fields. And we can't even pick on Kyle because he's not here. But last section, that's what we did, is we used slope fields to sketch solution curves of differential equations. But now what we want to do is we want to see how can we solve these analytically. So for example, if I have this differential equation, and if I'm looking at this because I think you're going to see that that's, well, it's not negative, one close to that on your worksheet. If I sketch the slope, and you can see it kind of, and so in other words, I could put the negative on the x, and I could look somewhere like, say, where x is -1, and then y would be a +1. In other words, all I'm going to do is put values in for the slope, and I put those little lines to represent the slopes. As you can see by the slope field, or hopefully you can kind of see, these are circles. So this gives us the solution, x squared plus y squared equals c. So you kind of remember that's the end of a circle. And we could actually check that these circles are solutions by derivation. So what separation of variables does is exactly what it sounds like. You separate the variables. And so if I have something that looks like this, I'm going to get all the y's, dy's on one side. I'm going to get all the x's, dx's on the other side. And then I'm going to integrate. Okay? So that's all I've done here. And it doesn't matter where you take the negative. And you're even going to see with constants, I see you sneaking in, you're going to even see with constants, it doesn't matter which side you put it on. But so I brought the y over here, so y dy, I brought the dx to the side. And then the next step is you integrate both sides. And so remember, when you integrate, you're finding the antiderivative, y to the first power. You add 1 to the exponent, divided by the same thing. This over here, of course, I have negative x to the first power, so x squared over 2. So hopefully you're kind of getting the antiderivative stuff down.
Why does it k?
But you like c's for constants?
Yes.
Yes, okay. I used a k for a constant because if you remember when I showed the x squared plus y squared equals c. So I already used that letter. That letter was used up.
That's for the tree.
Okay. All right, and so then if by looking at this with my separations of variables, I can multiply every one of these by 2. I, of course, can move that to this side, and sure enough, I get the solution, okay? So to be able to prove something, if I give you something like this, then you separate the variables, you integrate both sides, and then you see, and in this, I can let c equal 2k. So in other words, this is just any constant, okay? It's 2 times the constant. All right, so if I want to derive the general solution of this following differential equation, first thing I'm going to do separation of variables is I'm going to separate these variables. So in other words, I'm moving the y to the other side. So you can say I'm dividing it or multiplying by 1 over y. I'm moving the dt to this side, and again, this k is my constant. I integrate both. So integrating both sides, my constant can come out front. And so 1 over y, remember this is the antiderivative. How I would have gotten it was by taking the derivative of ln. So working backwards, I could see that that would be 1 over y. And then my constant here, most students kind of like to put a 1 right there, which is fine because then that shows you that the antiderivative would just be t, because if I took the derivative of t, I'd get 1 back. And now I have to take this and I have it for y. How do you do that? Yeah, it's just e. Yeah, so in other words, what Justin's saying is take each one of these and raise it, take it e raised to the power. And so that, of course, we kind of say that cancels out. I get y. There's nothing wrong here because these have the same base. If I'm adding exponents, I can separate these and multiply. And the reason I do this is this piece right here is just a constant. Okay, this is the only thing that in variable. And so I could let this equal, this piece right here, I could just let it equal any, and you'll see in your textbook they use the letter a. So what I end up here with is an exponential function. So this differential equation, the solution to it is actually an exponential function. And this one you will see is on your handout for today.
Is Is it half-lives?
Yes.
Half-life?
Yeah, and so this, in fact, this will do a little bit the last week where we get into more exponential functions, what you could do with them, the decay function, and so you're going to certainly see these. All right, here's another one. So we continue and we do the same thing, find all solutions for this. So the first thing I'm going to do is take this piece and move it to this side that has the y in it. I'm going to leave this side alone, integrate both sides. And so here's my integral. If I have this is like the 1 over y, so my log. And so this becomes ln of this. This, of course, is still my kt plus c. Doing the same thing, solving for y. I just didn't show that I did this, but
Could you slow down just a little?
I can go faster, yes. Yes.
Please?
Yes. And so what you'll see is after I integrated both of these, I'm going to solve for y. I just kind of didn't show you this step, but I did the same thing as I did in the other one. I took e and raised it because then that cancels, okay? And so we end up with this. That canceled out. And then I did the same thing here. And the only reason why I'm doing this is because it's not in terms of my variable. And I see it's always nice to pull constants out front. So that's all I'm doing. This is just a constant, because remember, e is just a number, and in this case, raised to whatever this constant is. All right, and so then finally, the last step is throw that to the other side, and so this would actually be a general solution for my differential equation. So all you're doing on these, and you're going to see the y when we get to the next section, is when you have two variables and you're trying to find the original equation they came from, you have to separate them, integrate one side, integrate the other side, solve for y, and then you get your actual equation. So now, hopefully, everybody